From the simulation that you just did, you should have learned that Avogadro's law states that the number of particles of a gas is directly proportional to the volume of the gas. Now this is going to be really interesting and helpful to us, but we're of course not going to talk about number of particles of a gas, right? Too many particles in a reasonable size sample. So instead we're going to talk about moles. Because the mole is more or less the representation of the number of particles of a gas. So remember that moles has the symbol MOL, and we think maybe we'll use that. Well, no, not in this chapter. For this chapter and for this chapter only, the mole is represented by the letter N. Okay, and volume of the gas will still be V. So, we now have the number of moles of a gas is directly proportional to the volume of a gas. This is really powerful for us. It allows us to say things like 1 mole of hydrogen will have the same volume as 1 mole of carbon dioxide gas. So the identity of the gas really isn't important. It's just the number of particles of that gas. Now, experiments were done, and it was determined that 1 mole of a gas, and this is again any gas at all, equals 22.4 liters. So 1 mole of a gas takes up a volume of 22.4 liters. Now, this is at standard temperature and pressure, which we'll do more with later. But for now, we'll just kind of keep this guy in the back of our brains. Okay, what I'm going to do now is take this N is directly proportional to V and combine that with the other proportionalities we have. Pressure is inversely proportional to volume. Pressure is directly proportional to temperature, and volume is directly proportional to temperature. I'm going to take all these and I'm going to combine them. Okay, from here, I'm going to start with pressure times volume. Okay, and I'm going to say that that is directly proportional to temperature and the number of moles. And by now you should know that in order to go from an equality or proportionality to an equality, all we have to do is add a constant. Right? And this constant actually turns out to be a little bit special. If I solve for that, and I use this information up here, I'm going to get something very interesting. So at standard temperature and pressure, so that's 1 atmosphere, and standard temperature is 273 Kelvin. 1 mole of a gas equals 22.4 liters. Now, notice this never changes. So K is a constant for every gas under every single situation. And if we solve for that, we're going to get 0.0821. Now our units are going to be kind of a mess. It's going to be liters times atmospheres over moles times Kelvin. All right, and this is so special, this constant is so special that it gets a special symbol, R. R stands for the ideal gas constant. And I can take R and substitute that in up here, and I will get PV equals nRT. And this is the ideal gas equation. Oh, slow down, Mr. Ryan. Okay, and this constant, the ideal gas constant, is always a constant. Here we have a problem. Now, when we look at this problem, one thing that might strike you as a little different from the problems you've seen in the past is that this has a gas under only one set of conditions. Okay, so if you see something under one set of conditions, you should be thinking to yourself, ideal gas law. Okay, so I have a volume, I have the number of moles, and I have a temperature. So my volume is 2.07 liters. My number of moles is 2.88 moles. My temperature is given in degrees Celsius, so remember I'm going to need to add 273 to that to convert it to Kelvin, so that's 295 Kelvin. R is a constant, 0.0821 liters times atmospheres over moles times Kelvin. And I'm trying to find the pressure. Okay, these are all related by the ideal gas law, PV equals nRT. And here I'm going to solve for pressure. Sorry, over V, not. So that's pressure is nRT over V. I got that just by dividing both sides by V so I could isolate pressure by itself. Now, when using this ideal gas constant, I find that it's helpful to either start or end with that. And the reason for that is you can set this up as its own thing in dimensional analysis. So 0.0821 liters times atmospheres all over moles times Kelvin. Okay, and now I can just take my line and extend it. Okay, my number of moles is 2.88 moles. My temperature is 295 Kelvin. And my volume is 2.07 liters. Okay, and when I do the calculations for this, I get 33.7. Now let's take a look at our units really carefully. Moles cancel out, liters cancel out, Kelvin cancel out. So we're going to get our pressure in atmospheres. You want to do that check that all your units cancel out before you do your calculation, okay? Make sure that your units cancel out before you do your calculation. So here you have a problem using the ideal gas